All right. Today we're on chapter 8, hypothesis testing. This is really the meat of statistics. You can do the math on determining the probabilities of things happening. Hypothesis testing basically just tells us, is something worth doing or not? Is there enough evidence to say there isn't worth it, or is there enough evidence saying it's not worth it? Like all things in statistics, we're never 100% positive. We always leave room for that chance that we're wrong. All right. This first section is pretty definitely heavy. It's a lot of new vocabulary in this. Um, but as always, if you develop questions, keep emailing me, and I'll keep answering those questions. All right. Researchers are interested in answering many types of questions. These questions are stated as claims about a population. The decision-making process for evaluating these claims is called hypothesis testing. Ooh, supposed to be a Y there. Researchers define the population. Under study, state the hypothesis or claim to be investigated. Set the significant level and select a sample from the population. Collect the data. Run the statistical test. And reach a conclusion. We will consider 3 methods of performing a hypothesis test. They are a traditional method, the p-value methods, which is really just probability, and then the confidence of interval method, what we've been seeing in the last couple of chapters. To start this off, we'll talk about the steps of a hypothesis testing for the traditional method. So in the first objective, we want to understand the definitions used in hypothesis testing. All right. So the definition of a statistical hypothesis is a conjecture about a population parameter. The conjecture may or may not be true. That's what you'll be testing. There are always 2 sides to a conjecture, the conjecture and its complement. So basically, I can say it's raining outside, and its complement would be it's not raining outside. For the null hypothesis, it is symbolized with H naught or H0. Uh, is a statistical hypothesis that states that there is no difference between a parameter and a specific value, or that there is no difference between 2 parameters. Basically, what we're doing is typically come up with a hypothesis stating that we think that something will be greater than or less than the mean or flat out different from the mean. The null hypothesis basically just states that there is no difference from what we're testing versus what the population mean is, or whatever it is that you're looking at. Now, depending on your claim could be supporting the null hypothesis or what we call the alternate hypothesis, where the alternate hypothesis is basically, yes, it's greater than the mean, and the null hypothesis is your hypothesis could be, I think that it is greater than the mean, or I think there's no change. And then you would go with the testing, and then that will kind of determine, all right, what was more correct? What evidence do we have to support each case to determine if we can deny our hypothesis or not have enough information to accept our hypothesis? All right. So with that being said, the last one right here is alternative hypothesis, symbolized with H1. It is a statistical hypothesis that states the existence of a difference between a parameter and a specific value, or states that there is a difference between two parameters. So again, I'm talking about the mean, but we could be specifically talking about standard deviation, variance, the mean, the median, things like that. So just any type of parameter, we're saying that there is an existence, that there's a difference between what we have versus what we're testing. So basically, again, the null hypothesis always states that the parameter is equal to a specific value or to another parameter, and the alternate indicates change. So the alternative hypothesis claims that the parameter is either not equal to, greater than, or less than a specific value or than another parameter. So you can test that something's greater than, less than, or just flat out, it's just not equal to this. It's either greater or less than. All right. So in our second objective here, we're going to talk about how do we state what the null and alternate hypothesis is. So in our first example here, we just want to simply state, I think it has all the solutions. Oh, we have the blanks. Okay. We're going to state which one is the null and alternate hypothesis. So looking at A, it says the average age of first year medical school students is less than 29 years. So basically what's going to happen is, to make this real simple, and then we'll fill in the blanks, this guy right here would be your null hypothesis, because you're saying that there is no change with the null. So we're saying that the average age of a first year medical school student is 29. Now, your alternate hypothesis would be this statement, that the average of the first year medical student is less than 29. So the null will always be equal. And then the alternate is basically something different. It can be a less than, it can be a greater than, or it could be just not equal to. So when we look at how they answer the question here, it says the average age of first year medical school students has decreased from 29 years. The researcher knows a previous value for the average age and believes that the age has decreased, right? So that is the hypothesis that we are going with. Thus, no change would mean that the age is the same as it was before. So the null hypothesis is the average age of 29. So you'll see that the null hypothesis, H0, is stating that the mean is equal. So the null will always be pretty much the equal sign. The alternative hypothesis is that the average age is less than 29 years. So you'll see now we have the H1, and now we're saying that the mean is less than 29. The test indicates that the only change of interest is less than 29. So the test is called a left tail test, because again, we're looking at, think of it like this. It's your normal distribution. Here is your null, and then this would be your alternate hypothesis, stating that we think it's less than 29. So this is a left tail test. Okay, let's do some more. All right, so on part B, it says the average number of seasons in which an NBA player participates is 471. So this, again, you're basically stating that the null hypothesis is 471. And for it to not be 471, your alternative hypothesis would be not equal to 471. So again, when you're, whatever they say the average is, we're stating that the null hypothesis will always be that. And you can kind of see that here. We'll kind of go through this all together. But we see that the null hypothesis is stating that the mean is equal. And the alternate hypothesis is stating that it's not equal to, because this is really what we're looking at. We're stating that the average number of seasons in which an NBA player participates is 471. That is really what we're looking at. So this would actually be our claim. And then this would be the one that we're testing. So as you can see, it says the average number of seasons in which an NBA player participates is 4.71 seasons. The researcher is concerned with the number of seasons NBA players play. Has the number of seasons increased, decreased, or remained unchanged? A previous study indicates that the average number of seasons of the population of NBA players. So the hypothesis for the claims are, so you get the null hypothesis is that it's equal. The alternative hypothesis is that it's not equal. This test indicates the change could be more than or less than 471 seasons and is called a two-tailed test, because now what we're looking at is here's our null. Oh, that's an H. Here's our null, and then our alternative hypothesis could be on either side. We're just trying to state, is there enough evidence to say that it is not equal to 471 or 4.71? Alrighty, moving to C now. On part C, it says the average number of monthly sessions on the internet by a person at home has increased from 36. So we see 36. So again, our null hypothesis would state that the mean is equal to 36. Again, null hypothesis always the equal. And then since it is I guess it says here increased from 36, it would mean that the null hypothesis is greater than 36. So the change of interest is an increase from 36 or a number of sessions greater than 36, and this would be called a right tail test. Again, here is our null, and then this would be anything that lands in that region would be considered a alternate. Now we're going to learn is a certain region, so even though this is the mean, we'll have a little bit of a window here that we can say, well, if it's inside this window, we don't have enough evidence that it truly is, but if it falls out a certain window, then we can say it definitely is. But we'll talk about that later on. All right. Part D now says the average cost of a basic cell phone plan is at least $79.95. So once again, the word at least means equal to or greater than. Thus, change would mean that the average cost is less than $79.95. So once again, our null hypothesis here would be that the mean is equal to 79.95, and anything that would be greater than would actually be a true statement. So again, we're saying the average cost of a basic cell phone plan is at least 79.95, so it could be this or more. So we find out that anything less than 79.95, this would be a dramatic change. So again, statement says at least this amount. So that would mean this amount or greater. So the alternative hypothesis to disprove this has to show that the mean is less than 79.95. And again, our null is always going to be equal to. And again, this would be considered, because it's a less than now, would be considered a left-tailed test. All right, part E says the average weight loss for a sample of people who exercise 30 minutes per day for 6 weeks is 8.2 pounds. So again, once again, our null hypothesis would be that the mean is equal to 8.2. When we test people, that's not going to change. We don't see any less than or greater than or at least or anything like that. So our alternative hypothesis would basically have to just be, well, if there's any change at all from that state. So null would be equal, and then the alternative would not be equal. And because it's a not equal to, this would be called a two-tailed test. All right. So hopefully that gives you enough examples to understand how to claim the null and alternative hypothesis by some certain statements. All right, here we go. So here's a little chart to help you out. So again, a two-tailed test would basically be that anything that states that the null hypothesis is equal to something, but the alternative hypothesis is not equal to something. And then we could look at, I think this, I want to say this deals with probability. I forgot what this symbol is, but I know we'll see it later on and that'll recall. But we'll for now we'll just call it any parameter instead of just the mean. So any parameter would be equal to the null hypothesis, and any parameter would not be equal to the for that alternative hypothesis. For a right-tailed test, you'll notice that the null hypothesis is always equal. That part doesn't change. But for a right-tailed test, remember that's going to be on the right side of a distribution. So that'd be anything greater than the mean or anything greater than the parameter. And for a left-tailed test, that's everything on the left side. So that's going to be anything that's less than the mean or anything less than the parameter. And again, notice the null hypothesis is always stated using the equal sign. Right? The null hypothesis is the easy one. Alternative hypothesis, we just kind of have to read the vocab and see, all right, is this a less than, greater than, or just no change at all? When researchers conduct a study, they are usually looking for evidence to support their claim. Thus, the claim should be stated as the alternative hypothesis. And the alternative hypothesis is also called the research hypothesis. All right, so a claim can be the null or the alternative hypothesis. It just depends on what you're trying to determine. A lot of times, if you're trying to determine if something's less than the mean, greater than the mean, you're going to go most likely with the alternative hypothesis. But if you're trying to prove that the mean is equal or anything like that, then you'll go with the null hypothesis. If you wanted to claim that also that just is flat out change, then again, you'll go back with the alternative. So whatever the research study is that you're trying to prove, if you're trying to prove that it is equal, it's null, and not equal to will be the alternate hypothesis is what you end up trying to prove. According to the research, you don't have to come up with this opinion. You do the math of what the researcher is trying to determine. Alrighty, here we go. All right, so however, statistical evidence only supports the claim if it is the alternate hypothesis, and statistical evidence can be used to reject the claim if the claim is no hypothesis. So if null hypothesis is what we're testing, and the work claims the alternative hypothesis, then we will, which was the null hypothesis. After stating the hypothesis, the study is designed. The researcher selects the correct statistical test, chooses an appropriate significant level, and makes a plan for conducting a study. So in example 8.1 part E, the researcher selects a sample of patients who will exercise 30 minutes a day for 6 weeks. At the beginning and again at the end of the 6 weeks, the weights of the people are measured. So that was how it was going to be done. So recall that the samples of a specific size randomly selected from a population, the means of the samples will vary about the population mean, and the distribution of the sample means for sample sizes of 30 or more will be approximately normal. Even if the weight loss is exactly 8.2 pounds and the null hypothesis is true, the mean of the weight loss for a sample of people will not, in most cases, be equal to the population mean of 8.2 pounds. And again, there's a lot of variables there as well that could have also caused the more weight or less weight. All right, there are two possibilities. The null hypothesis is true, and the difference between the population mean and the sample mean is due to chance. So again, the null hypothesis is true, and the difference between the population mean and the sample mean just happened to be by chance. Or the null hypothesis is false, and the sample came from a population whose mean weight loss is not 8.2 pounds, but in some other values that is unknown. So again, the values and variables there made it not so, and therefore we said it was false when maybe it was true. And you'll see some error in that as well. We'll get to that. So the greater the difference between the claimed population mean and the sample mean, the more evidence there is for rejecting the null. So if it is really close, it's hard for us to say we need to reject it. But if there's a huge difference between what I got and what the mean population mean is, then I can go, that just gives me more evidence and more confidence to say, yeah, we're rejecting that. It's definitely not equal to 8.2. The probability that the sample came from a population with a mean of 8.2 decreases as the distance between the mean is greater. Again, the probability that the sample that came from a population with an 8.2 decreases as the distance between the means is greater. So as the means getting bigger and bigger, the chances of me getting something that's going to be 8.2 is going to get greater and greater as well. All right, so the decision must be made statistically rather than based on feelings or intuition. The difference must be significant enough and most likely not due to chance. So we need a big difference from the mean that gives us a confidence that will tell us we can reject the null hypothesis. There is definitely a difference here, but we need to determine what is that range. So let's get into a statistical test. Statistical test uses data obtained from a sample to make a decision about whether the null hypothesis should be rejected. A test value or test statistic is the numerical value obtained from a statistical test. That number, depending on what our range would be, tells us if we're rejecting or if we fail to reject. Decisions made to reject or not to reject the null hypothesis on the basis of the test statistics obtained from a statistical test rely on data from a sample drawn from the population. If the difference between the sample mean and the population mean is deemed to be significant, the hypothesis is rejected. Otherwise, we just say the null hypothesis is not rejected. So notice the wording there. If enough evidence, we're going to reject that hypothesis. But if there's not enough evidence, notice that we just simply we don't reject it. We didn't accept any hypothesis. You either simply reject it, and that's not saying that the alternative hypothesis is true. We're just simply saying that the null hypothesis is being rejected. But even if there's not enough evidence to say that the null hypothesis isn't true, we simply say we just don't reject it. We're not claiming that it's true. There's not enough evidence that says that we can reject it. So again, we never accept anything. We just simply reject or we do not reject. All right. So again, because sample data are used to decide to reject a null hypothesis or not, it is possible that an incorrect decision can be made, which is what I was talking about earlier. So let's talk about this error. really like to get all that together, and I don't know if it's going to let me. All right, so in reality, the null hypothesis may actually be true or may not actually be true. Regardless of actual truth, a decision to reject the null hypothesis or not is still made. Thus, there are two possibilities for a correct decision and two for an incorrect decision. If we reject the null hypothesis when it is true, this is an incorrect decision and a type 1 error. So let's say we do the math and there was a big enough difference that we were like, yeah, we can definitely reject the null hypothesis. But then we find out that the null hypothesis was actually correct. And again, it could be anything. It could be the sample size or the amount of data that we got, but we could end up making a type 1 error. The null was actually true. If we reject the null when it's false, we did good. We got a correct answer there. We rejected the null and it ended up being a false statement. If we do not reject the null and it is true, again, did it out there. We didn't reject the null, but we didn't accept it. We just didn't reject it and it ended up being true, so therefore we're correct. And then the last one, if we do not reject the null, so we say it is true, when it's actually false, this is an incorrect decision and a result in a type 2 error. So again, if you reject and it ends up being false, good job. If you fail to reject and ends up being true, good job. But if you reject when it was actually true, type 1. If you failed to reject and it actually ended up being false, meaning you said it was true and it actually ends up being false, type 2. So if you say false when it's true, type 1. But if you say false, you say true when it's false, type 2. Right? And here's another little chart here you can use as well to help you out. And let's see if I can get this on one page. There we go. There you go. So you can see, I think I went into this a little bit. Oh, well, you can see, again, if you reject the null, but the null is true, type 1 error. If you do not reject the null and the null ended up being false, type 2 error. If you do say it's false and it was false, that's correct. If you say it is true and it's true, that's correct. All right, so again, this kind of lines it out as well. So a type 1 error occurs if a true null hypothesis is rejected. So again, if you're stating it's false and ends up being true, that's a type 1 error. A type 2 error occurs if a false null hypothesis is not rejected. So if we do not reject it and it ends up being a false statement, we now have a type 2 error. All right, let's look at another example now. We've done quite a bit of notes. In example 2, we're going to talk about medical research. So it says a medical research is interested in finding out if a new medication changes the pulse rate of a patient who takes it. Suppose the mean pulse rate for the population under study is 82 beats per minute. Then the null hypothesis is that there is no change in the patient's mean pulse rate from 82 beats per minute after taking the medication. So again, stating that the null hypothesis is that it's going to be 82. That's what it's going to equal. And then we'll state that the alternate hypothesis is that the mean pulse rate for patients after taking the medication is just simply not 82 beats per minute. So it could be less than or greater than. So we simply say not equal to 82. Identify the decisions that would be correct and which ones would be type 1 or type 2 errors. So here we go. So in this case, if the null hypothesis is in reality true, so it is equal to 82, then it is a correct decision to not reject the null hypothesis. So if null hypothesis is true, then we don't want to say it's false. In other words, the mean pulse rate for the population of patients is 82 beats per minute, and the sample mean is not significantly different from 82 beats per minute. The researcher believes that the medication does not change patient pulse rates. The researcher does not reject a true null and made a correct decision. Because again, we know that we found out that the null was correct after we stated that we did not reject the hypothesis. All right, let's look at the next one. Scenario. These are all different scenarios. So if the null hypothesis is in reality true, then it is an correct decision to reject the null. So if it was true and we reject it, stating that it is false, this would be a type 1 error. In other words, the mean pulse rate of the population of 82 is 82 beats per minute, but the sample mean that we got is significantly different from 82 beats per minute. And the researcher believes that the medication changes a pulse rate. The researcher has now rejected a true null hypothesis and made a type 1 error. Again, it was a true null and we said it was false. So that would be type 1. All right, here's another scenario. If the null hypothesis is in reality false, then it is a correct decision to reject the null hypothesis. If it is false, then for us to be correct, we better say it's false too. Again, you usually don't know if something's false or not until after the fact. In other words, the mean pulse rate for the population of patients is not really 82 beats per minute, but the sample mean significantly different from an 82 beats per minute. The researcher believes that the medication changes the pulse rates, and the researcher has rejected a false null and made a correct decision. All right, next scenario here. So if the null hypothesis, again, is in reality false, then it would be incorrect if we did not reject the null. So if it is a false statement and we do not reject it, we're basically stating that it's a true statement, then this is a type 2 error. So when it's false, but we said it's true. So in other words, the mean pulse rate for the population of patients is actually not 82 beats per minute, and the sample mean wasn't significantly different enough from 82 beats per minute, and the researchers believe that the medication did not change the patient's pulse rate. The researcher has now rejected a false null and made a type 2 error. All right. I think that was the last one. Nope. There's another one. Here we go. All right. Here we go. So this one says researchers make decisions based on sample data. If the evidence against the null hypothesis is strong enough, the null hypothesis is rejected. If the evidence is weak, the null hypothesis is not rejected. Their decisions to do not their decisions do not prove that the null hypothesis is true or false. We never state if something's true or false. We simply either accept or reject that null hypothesis. Statistics do not prove anything absolutely. Again, we're never 100% positively correct. Always leave a little room for us to be wrong. The only way to prove anything statistically is to use the entire population. So if we have the entire population, then we would need to do the statistics on the entire population, and then we know for certain that this is exactly whatever parameter we're looking at. Thus, it is important to decide how large the difference between the mean obtained from the sample and the hypothesized mean must be in order to decide whether to reject the null hypothesis or to not reject the null hypothesis. That's the next step. What is the significant level that I keep talking about? So, the level of significance symbolized by alpha is the maximum acceptable probability of making a type 1 error. So that is the probability that a type 1 error will make, right? So we're basically stating that, how happy are we? We have a 1% chance that we're going to make a type 1 error. Then we're pretty good with that. We are good with a 10% type 1 error. And then we would accept it. We have to determine how much of an error probability are we happy with, and then go with that when we try to determine what our significant level ends up being. All right, here we go. So statisticians usually agree on using 3 arbitrary significant levels. We're either good with a 10% probability of making a type 1 error, a 5% probability, and a 1% probability. Depending on the level of significance selected, if the null hypothesis is rejected, the probability of making a type 1 error is either 10%, 5%, or 1%. This depends on, according to who we work for, what are they happy with? Are they okay with a 10%, or are they going to be pretty darn confident? They're like, you have a 1% probability. Right? Well, again, we don't want to be wrong, but it's always that chance. All right, so in our third objective here, we're going to find these critical values for the z-test. So once a significant level is chosen, the corresponding critical value is selected from a table for appropriate test. If a z-test is used, the z-table on table E is used. Value of z that separates the critical region from the non-critical region. So we got to determine where is that region at, so we can determine if the z-score that we get is less than or greater than the z-score of our region to determine, are we going to reject it? Is it in the rejection zone or not? So here we go. So the definition, so the critical or rejection region is the range of test values that indicates that there is a significant difference and the null hypothesis should be rejected. If it does not fall outside of this range that we determine, then we just simply say there's not enough evidence to reject the null, so therefore we do not reject the null hypothesis. But if it falls outside of our region, then we can confidently, with enough significant difference, that we can reject the null hypothesis. All right. Our non-critical region. So the non-critical or non-rejection region is the range of test values that indicates that the difference was probably due to chance. All right. We have to leave that there is just we just happen to group and the change. So there wasn't enough evidence. Null hypothesis should not be rejected. Evidence state that all right, the critical value separates the critical region from the non-critical region, and the symbol for the critical value is CV. To give you a little bit better idea of what that means is, this is just going to be random. Let's say we are doing a two-tailed test. Here is our region of that we do not reject, and then anything that falls outside of this z-score, whatever that is on the left or the right, if it falls there, then we do reject. Some things we're just looking at this region, right? We're saying, is it larger than this? So if it's anything that falls in there, we reject it. Or if we're looking at this and everything that falls in this category, we reject it, and the rest of it is the safe zone. All right, that's kind of what I'm trying to get at, was we got to find out what region are we happy with. Anything that falls outside of that region tells us, okay, there's enough evidence. We can now reject this hypothesis. All right, so for an alternative hypothesis stating that the mean is greater than 40, that uses the greater symbol, or sorry, greater than symbol, the null hypothesis will be rejected only when the sample has a mean that is significantly greater than 40. Thus, the critical value must be on the right side of the mean. Then the test is called a right-tailed test. All right. And then alternatively, for an alternative hypothesis where the mean is less than 40, that uses the less than symbol, the null hypothesis will be rejected only when the sample has a mean that is significantly less than 40. Thus, the critical value must be on the left side of the mean. Then the test is called a left-tailed test. So definition of a one-tailed test. So a one-tailed test indicates that the null hypothesis should be rejected when the test value is in the critical region. If it's in the non-critical, then we do not reject. On one side of the mean, right? So it's either very little or very more. It has to fall on the left side or the right side, depending if we're dealing with a less than or less than or greater than. A one-tailed test is either a right-tailed test or a left-tailed test, depending on the direction of the inequality of the alternative hypothesis. To find the critical value, the researcher must choose a significant level called an alpha level. And remember that alpha is the complement of the confidence level, meaning, well, this says it right here on this next part. So suppose the medical researcher chose to use a 99% confidence level, and thus the alpha would be 1 minus 0.99. So therefore our alpha would be 0.01. The alternate hypothesis is that the mean pulse rate is greater than 82, so greater than 82, so we get a mean like this. Then the Z value is such that 1% of the area falls to the right, we're looking at a greater than, and 99% of the area falls to the left. Using table E, find the area value in the body of table E closest to 99% or 0.9900. In this case, the closest that we could get is 0.9901. Thus, the z-score that we're looking at is 2.33. So again, using that table E, this is as close as we can get. So basically, we're going to get a z-score of 2.33. So when we do our math to determine the z-score of the data that we have, if it ends up being greater than 2.33, we're rejecting the null. But if it ends up being anything less than 2.33, anything less, I mean, it could be a negative over here, then we fail to reject and state that there's not enough evidence to state that it's greater than, because that's what you're testing. You could get negative 17.8 over here. And if that would be the case, you're still not rejecting the null because there's not enough evidence to claim that it's greater than. So just keep that in mind. You got to determine where you're at. What's the safe zone for the situation that you're in or asked to be in? All right, so now suppose the medical researcher chose an alternate hypothesis that the mean pulse rate is now less than 82 beats per minute. So now we're looking at less than 82. Then the Z value is such that 1% the area falls to the left, because again, we're now doing a less than, and 99% of the area falls at to the right. This is what a left-tailed alternate hypothesis looks like. Using table E, we find the area closest to 1% or 0.011. In this case, the closest thing we could get is 0.099, and the value is negative 2.33. So in this case, again, what we're going to look at is if when we do our testing, does our z-score give us anything less than negative 2.33? If it does, we're rejecting the null. If it does not give us anything less than 2.33 and it falls on the region on the right, then we fail to reject. There just wasn't enough evidence to claim that it was going to be less than. When the research question is about whether the mean is different from a particular value, as in the case of an alternative hypothesis that the mean pulse rate is just simply not equal to 82 beats per minute, meaning we're looking at a two-tailed test, the researchers is conducting a two-tailed test, and the null hypothesis can be rejected when there is significant difference above or below the mean. All right, so let's kind of get into this next part here. So for a two-tailed test, the critical region is separated into two equal parts. So each having an area 1/2 of the alpha. So for instance, if we stick with this 0.01 as our alpha, then when a two-tailed test comes, we're looking for a z-score of 0.005 on both sides. So we look at the 0.05. I'll just keep reading here and I'll kind of explain. Is to the right and to the left of the mean, and then 0.05 to the left of the mean. The z-score to the left is found by looking up the z-score corresponding to the area of 0.005 on table E, and 0.005 falls halfway between 0.051 and 49. So therefore, we're going to choose the smaller one. So we'll go with the negative 2.575. If the z value is needed to 3 decimal places, or we can just simply just say negative 2.58 if we round to 2 decimal places. So again, if this is what we're getting for our left side, then the right side would just be the positive of that. So the value z-score on the right is the opposite of the left-hand z-score due to symmetry. Oh, hold on. Let me get this all the way up so we can see it. Due to symmetry. And thus it is either 2.575 or 2.58. So now what this means is for a two-tailed test to see if there is a region in which it can be different, if we find anything less than negative 2.58 or greater than 2.58, then we can reject the null. If it falls in between, we do not reject the null hypothesis. All right, so let's get into the steps of doing this. So steps for finding critical values for a specific alpha value using table E. So in step one, we are just going to simply draw the figure or the normal curve and indicate the appropriate area. This will help us determine if it's going to be a left, right, or two-tailed test. So if the test is a left-tailed test, the critical region will, with an area equal to alpha, will be on the left side of the mean. So if it's a left side one, this is what we're looking at. All right. If the test is right-tailed, the critical region with an area equal to alpha will be on the right side of the mean. So you'll look something like this. If the test is two-tailed, alpha must be divided by 2, and 1/2 of the area will be on the right of the mean, and the 1/2 of the area will be on the left of the mean. So you'll have one on each side of it. Step 2, so again, and what we're looking at as we draw our figure, you have a region here and a region here. All right, so in step 2, for a left tail test, we'll use the z value that corresponds to the area equivalent to alpha in the table E. For a right tail test, we'll use the z value of that corresponding to the area equivalent to 1 minus alpha, also known as the complement of alpha in table E. So notice in a left tail test, and you're right here, whatever this, if this is 0.5 or whatever, I can just go straight to that. But over here, if I'm looking at a right tail test and I want it to be 0.05, I need to do 1 minus that to get the 0.95 to get the correct value there. So that's why you have to do 1 minus that. And then for a two-tailed test, we use the z value that corresponds to the alpha divided by 2. For the left value, it will be negative. And then for the right value, we just use the z value that corresponds to the area equivalent to 1 minus alpha divided by 2. Or what I like to do is to simply just use the opposite of the left value due to symmetry. So if I get negative 0.58, then I know it's going to be positive 2.58. And again, it'll be a positive value. All right, so that's step 2. All right. So let's get into our fourth objective. We're going to state the 5 steps now used in hypothesis testing. So steps for hypothesis testing. Step 1, you will state the null and alternative hypothesis and identify the claim. So that's one thing we hadn't done yet, but we have been practicing stating the null and hypothesis. You must state what your null is going to equal to and what your hypothesis will be. Is it going to be a not equal to? Is it going to be a less than? Or is it going to be a greater than? Then we have to determine the claim. The claim is, what is the researcher wanting? Is the researcher stating that it's equal to? Then the null is our claim. Or is the researcher stating that it's not equal to, or it's less than, or it's greater than? If that's the case, then the alternative hypothesis would be our claim. Then step 2, we'll design the study, select the correct statistical test, which we haven't talked about yet, but we will. And then we will choose a level of significance. Which will then determine what is our probability of getting a type 1 error, sorry. Define that population, and then determine how the sample is selected and decide the methods used to collect the data. We will then conduct and study and collect the data, then evaluate the data, tabulate the data, perform the statistical test and decide whether to reject or not to reject the null hypothesis. And then we just summarize the results with a good little couple of sentences stating what have we found, what are we stating, what are we answering, things like that. All right, so that's our steps of our hypothesis testing. Now, solving hypothesis testing problems using the traditional method, which is what the whole point of this section was, but we had to get through a lot of definitions to get there. Just like before, first step, state the hypothesis and identify the claim. Find the critical values from the appropriate table, compute the test values, make the decision to either reject or not reject the null hypothesis, and then summarize the results. You'll notice that most of these testings kind of have the same steps. It's just that test in the middle is going to look slightly different. So if we summarize the results of a hypothesis test, this is what will happen. So if my decision is to reject the null and my claim was the null. So again, the null is always what it's equal to. And if I'm claiming that the mean is in fact equal to, if that's my claim, is the null, then I say there is enough evidence to reject the claim. If I'm deciding, and whatever the claim might be, if I'm deciding to reject the null and my null was the claim, there's enough evidence then to reject the claim. Now, if I'm rejecting the null, but my claim was the alternative, then I state there is enough evidence to support the claim. Because if I'm rejecting the null, then I'm stating that the alternative must be true. So I'm now stating there is enough evidence to support the claim is true. Now, if I do not reject the null and the null was my claim, then it's a little bit of the same concept. There is not enough evidence to reject the claim. So again, if I reject it and that was my claim, then there is enough evidence. If I do not reject the null and the null is my claim, then I simply just say there is not enough evidence to reject the claim. So again, I'm not accepting it. I'm just saying there's just not enough evidence to reject it. If I do not reject the null and the alternative is my claim, and I'm basically stating that the alternative is wrong, then I say there is not enough evidence to support the claim. So again, notice I'm never really going with anything. I'm either saying there's enough evidence to reject it or there's not enough evidence to reject it. But I'm never accepting anything. All right, so statistical decisions are not a proof. Statisticians only state that there is or is not enough evidence to conclude that a claim is probably true or false. Nothing is actually proven. The only way, again, to prove something would be to use the impossible, oh, my bad, the entire population. It is usually impossible or impractical to do this. especially when the population might be the entire country or large enough. All right, so let's do one last example. It is kind of long, but let's do it where we're putting all this together. Still not putting any tests, but just are we able to write it out correctly? That's where we're kind of practicing right now. So in example 3, we're going to talk about eggs and your health. So the incredible edible eggs does not increase a person's blood serum cholesterol. 500 in a study that lasted for 2 years. The participants or a moderate egg group. The blood serum cholesterol checked at the beginning and at the end of the study. Overall, the group's levels were not significantly different, and the company reminds us that eating eggs is healthy, done in moderation. Many of the previous studies relating eggs and high school and high cholesterol jumped to improper conclusions. And we're going to answer these questions. So I'm not just going to name them here. I'm just going to go to where we have room to write. Here we go. So this first part of the question is, why did the company conduct the study? So when we go back and we read it, we'll see that the company wanted to show that moderate intake of eggs does not result in high blood serum cholesterol. Basically, they're saying in moderation, eggs are not going to change your blood pressure or cholesterol. So here we go. So it says the company wanted to show that moderate intake of eggs does not result in high blood serum cholesterol. All right. The second question, identify the population under study. It said in there that it was the population of American adults. So the population, starting to glitch. Give me a second. So the population is American adults. So number 3, what is the research hypothesis, and is it the null or alternate hypothesis? So what we can see is that the research hypothesis is that eating eggs in moderation does not increase a person's blood serum cholesterol. This would indicate that the null hypothesis and the alternative hypothesis states that so that would basically be the null. And the alternative hypothesis states that eating eggs in moderation does increase blood serum. So here we go. So again, the research hypothesis is that eating eggs in moderation does not increase a person's blood serum cholesterol. And since it's stating that there is no change, then that would mean that the research study is the null hypothesis. And the alternative hypothesis states that eating eggs in moderation does increase blood serum cholesterol. So number 4 then says, was a sample collected? Now, in this one here, the article does not state how the participants were selected, only that the group was separated randomly into those eating eggs in moderation and those of not eating eggs. So that's all that we're really told. So again, it says the article does not state how the participants were selected, only that the group was separated randomly into those eating eggs in moderation and those not eating eggs. So that's the only thing that we were able to see there, or at least it told us. All right, question 5 says were data collected? If so, what data? And we can see data was collected, and it was the blood serum cholesterol levels for each group were checked at the beginning and at the end of the study. So data was collected. Blood serum cholesterol levels each were checked at the beginning and at the end of the study. Number 6 says, were run? If so, was it a left or two-tailed test? And we can see, yes, statistical tests were run, and it was a right-tailed test because we increased our cholesterol levels. So statistical